Hi everyone. Today we'll take a look at direct proof. With the textbook definition, we have a direct proof is a way of showing the truth of a statement by representing a series of established steps, right? So, like I said in the introductory video, what we're trying to do is we're trying to use variables, right? We're trying to use variables, and we're also trying to show that left hand side is equal to right hand side. Oftentimes, you will be asked to do this, okay? So this is like the two key points that you need to know for direct proof. Okay. Now, one more thing I want to mention is, there are a wide variety of questions that can come in this chapter. Okay. So I'm not going to try and cover every single one of them, but what I'm going to try to do is I'm going to try giving you guys a variety of different aspects that a question can be asked from. Okay. And what you're going to try to do is you're going to try to pick up on those small things that can help you solve a question which you've never come across. Okay. Again, like I said, there's a wide variety of questions that can be asked, right? I can't cover every single one of them. And plus, it doesn't make sense to cover every single one of them because it's a huge pool of different types of questions. I can ask questions from sequences and series, a proving question from sequences and series, or something a little bit more advanced even, right? So it's limitless. So that's what you're going to try to eat. What you should do in this video is just try to pick up on the small different techniques that I use throughout every single question, right? And try to implement them when you try to solve the questions, right? Because those are the small techniques that will come handy when you try to solve the questions later on. All right, let's look at the first example. This question says, prove that the sum of any two odd integers is even, right? Now, obviously, if you start by, saying that, okay, let's take any odd integer. Suppose we take 5 and we take 7 and we add them up and we get 12. Oh, this is even, right? This is odd. Both of them are odd, and thus we have proved no, this is incorrect, right? What you're doing is you're only taking a specific case of 5 and 7 and showing that it satisfies this condition, right? We're not supposed to do that. No, this is a big no, right? Like I said previously, we're trying to use variables, okay? So how can we do this in terms of variables, right? Okay, so this is the important part. That's where this is the technique that you should be using every time moving forward. Okay, so what are we given? We're given that the sum of any two odd integers is even. Okay, that's what we have here. So how can we represent an odd number with variables, right? That is the key thing to know here, right? So if we try to represent any odd integer, what we can say is we could write it as 2k plus 1, right? Where k is any real number for that matter, right? Now if we multiply any number, whether it's an odd number or an even number, by 2, if we multiply it by 2, right, we get an even number, right? We take 2 times 3 is 6, that's an even number. 2 times 2, 4, that's an even number. 2 times pi, 2 pi is also technically can be considered an even number, right? But however, we're talking about integers, so let's ignore pi here, right? Any integers like 1, 2, 3, minus 1, minus 2, minus 10, right? 17 times 2, 34, that's an even number. So, right, what when we do 2k plus 1, we get even numbers, okay? But when we do 2k plus 1, when we add 2k plus 1, we get an odd number. So, right? Even plus 1 actually gives us an odd number, right? 4. 4 is an even. We add 1, we get 5. That's an odd number, right? 6 is an even number. We add 1, we get 7, which is an odd number, right? So if I just want to give you a small summary of what I just said, I can say that if we have 2k, we have an even number, right? Everyone, when you think of 2k, you think of basketball, whatever, right? You can remember it that way, maybe if that helps you. And we have 2k plus 1. We have odd. Okay, so this is the key thing to know here, right? So what the question is asking us is that it's asking us, sum of two odd integers. Okay, so we can take maybe integer number 1 is here. Integer 1 is maybe 2k plus 1. And integer 2, we can take any other variable for that matter. It doesn't matter, right? We can put 2n plus 1, right? It doesn't matter. It can be 1 and 99 for that matter. We don't care, right? This could be 1, this could be 99, k can be 0 here, and k can be, n can be whatever. So Now, what we said, the sum of two odd integers. Let's add them up, right? So if we add them up, what do we get? We get 2k plus 1 plus 2n plus 1, right? Let's simplify this a bit more. So we get 2k plus 2n plus 2. Now, if we have to show that something's even, right? I just said that, we need some 2 times k form, right? So why don't we factorize a 2 from here? So if we factorize a 2, what do we get? We get k plus n plus 1, right? Now, doesn't matter what this inside portion is, right? Let me put this in pink right here. This part doesn't matter. Okay, you know what? Instead of using a curly brace, I'll use a straight line. So, like I said, whatever this is, it doesn't matter because it's being multiplied by 2, right? When an expression, whether it's when an integer, an odd or an even, is multiplied by 2, it becomes even, right? So this could be anything. We don't care. But because it's being multiplied by 2, it's an even integer. So now we just proved that the sum of any two odd integers is an even integer. So if I want to write it formally, I could just finish it off by saying hence proved, right? That's it. Next question. Prove that the square of any odd integer is odd. Okay, this is quite similar to the previous one, right? The key takeaway from the previous question was that if we have an even number, we do 2k. If we have an odd number, we do 2k plus 1, right? That's the technique that we used, right? So now it says the square of any odd integer is odd. So if we have any odd integer for that matter, we can take 2k plus 1. And it's telling us that if we square it, right? So if we square this should come out to be odd. Now now that we squared it, let's expand it. So what do we get? We get 4k squared plus 4k plus 1. Right? So how do I show that it's odd, right? I need some form of this 2k plus 1, right? So what I can do is I see this 1 right here, right? And now I need 2 times some, variable plus 1. So what I can do is I can factor out a 2 from here, just this part. So if I factor out a 2, what am I left with? 2k squared plus 2k, and then outside plus 1. So now this, I'll put this in yellow. This can be, treated as a different entity altogether. Okay? So if we treat this as a different entity, what do we get? We're actually just getting, if I just put this, as a capital N maybe, right? So what I get, 2n plus 1, right? I'm getting in that odd form, right? So because I can, I substituted this entire expression 2k squared plus 2k with n, just to simplify, just to, make it easy on the eye, right? I just proved that it follows the form of 2k plus 1, and thus it's odd, right? Hence proved again. So, you can leave it at this point also. This is also good, right? You don't need to do this. If you just show, to the examiner, right, we have 2 times 2k squared plus 2k plus 1. That's enough. You will be awarded the necessary marks, right? Again, very simple question, quite similar to the previous one where we had 2k plus 1. I just want you guys to get in the habit of this. That's why I put in this quite similar question. Next question. Prove that 2n minus 1 whole cube plus 2n plus 1 whole cube is equal to 16n cubed plus 12n. Hence, or otherwise, prove that the sum of two consecutive integers is divisible by 4. Okay, so before I begin, I just want to mention this language right here that this question says, right? It says hence or otherwise, right? So this question, first of all, can be treated in two parts, right? Part A and part B, right? That's how you'll have the question in the IB as well. So first they'll give you maybe this part may be worth 2 marks or 3 marks, and this part will be worth 4 to 5 or even 6 marks depending on the difficulty, right? So this part obviously we have to show, right? You can clearly see it's in LHS is equal to RHS, right? And now if you guys get confused in this notation, I can rewrite it. So 2n minus 1 whole cube plus 2n plus 1 whole cube is equal to 16n cubed plus 12n, right? This is a simple LHS is equal to RHS, which I previously told you, right? However, this part says hence or otherwise, prove that the sum of two consecutive odd integers is divisible by 4, okay? This is supposed to say divisible by 4, okay? So now what here when you have hence or otherwise, either you use the thing that you learned from part A and show and solve part B, or you can do it some other way as well, right? It's completely perfect, right? Doesn't matter. Sometimes you might just have hence and you might not have otherwise. So when you just have hence, then you have to use what you know from part A and move forward. Okay, that's the key part. Now, one more strategic, tip that I want to share with you is that when you have, suppose you have part A, part B, and it says hence or otherwise, right? Now that's an advantage in my opinion, because if you can't prove this for some reason your algebras, you keep making some mistake, or it's some other, maybe it's not even algebra, it's trigonometry, and you keep messing it up, or you don't know what to do, right? So what you can do is you can take advantage of that and just do part B because it says otherwise, if you can, right? Provided that you can do it some other way, right? So that's a big advantage in my opinion. And these questions, at least, you can get some marks. You don't have to lose out on every single thing. So if this was maybe like 6 marks or 8 marks, you might even get 4 marks for just being able to do part B, right? Obviously, if there's just only hence, then kind of bounded to first doing this and then doing this, right? Now, again, there's a slightly different thing. It won't ask you like some here. It says prove that. So you've already got the result here, right? Oftentimes you might not even have the result, so you might be asked to simplify it first and then do the hence part. So here you already have a bit of help because you can see this and then you can work forward with it. Like this is kind of like the answer. It's to part A, right? It says show that or prove that, right? So these are just small things that you should be aware of as you move forward, or when you do past paper questions, or when you're even sitting in an exam, right? These are small things you want to think about constantly, so that it just makes your time during the exam much easier and able to actually attempt every single question and get a decent get a decent score or be able to solve all the questions for that matter. Right. Okay. Anyways, let's get started with the question. So first part says, prove that 2n minus 1 whole cube, 2n plus 2n plus 1 whole cube is equal to 16n cube plus 12n. So let's go ahead, we just have to do simple LHS equal to hard. So I'm just going to simplify LHS, right? Because it's the more complicated term. I can't go from 16n cube plus 12n to this expression right here. But I can go from here to here, right? I can go from LHS to RHS. So let's go ahead and do that. So if I do that, what do I get? I get 2n minus 1. I'm going to do it this way, right? 2n minus 1 times 2n minus 1 plus 2n plus 1. If you know binomial theorem, you can apply it here. If you don't, then you can do it this way. So binomial theorem is something I'll probably take in after permutation combination. So from after proofs, we'll have permutation combination, and then we'll have binomial, right? So let's if I expand this part just maybe this much here and this much here, right? What am I left with? I'm left with 4n cubed minus 4n plus 4, right? And then we have 2n minus 1 plus 4n cubed plus 4n plus 1. Sorry, it's actually 4n squared, not 4n cubed. So 4n squared into 2n plus 1, right? I'm just solving the LHS. I can just put, the therefore statement. So I'll just write left-hand side. Okay. So now if I simplify this, what do I get? I get 8n cubed, right? Just multiplying 2n on every single term. So I get minus 8n squared plus 8n. Then I do minus 1, so I get 4n squared plus 4n, and then I get minus 4, right? So this was this part, left part that was simplified. Now let's simplify this part. So what I get is, again, 8n cubed, then I multiply this, so I get 8n squared, and then I get, then I get 2n. Okay? I think I've made a slight mistake here, and that mistake here is right here. So this was supposed to be 4n plus 1, right? And then if I simplify this a bit more, what do I get? I get 1 and 2n, right? So I get not 8n, I get 2n. And then again, if I simplify here, I don't get, minus 4, I get minus 1. So just some corrections here. Okay. So I get plus 2n, and then now if I multiply it by 1, so I get plus 4n squared, and then I get plus 4n and plus 1, right? Now just, I can see some numbers that can easily cancel out. So I'll just change the color here. And I'll put, peach. So I get minus 8n squared plus 8n squared cancels off, minus 1 plus 1 cancels out, minus 4n squared plus 4n squared cancels out, right? So now if I simplify this a bit more, what I get is 8n cubed plus 8n cubed, which is 16n cubed, right? 2n and 2n plus 4n plus 4, and that gives me, sorry, okay, if I do, keep it simple, 2n plus 4n, 6n plus 2n, 8n plus 4n is 12n, right? Which is the right-hand side. So this is the left-hand side. Now it's equal to the right-hand side, so we can say LHS equals RHS. And that's part A, right? Again, all you saw is it was just, kind of lengthy algebra, right? There was nothing special here. There wasn't any conceptual knowledge, any, property that you were supposed to be aware of. Just simple algebra, and you were just required to, use your basic knowledge of simplification and get to part A. All right, let's look at part B now. Part B says, hence or otherwise, prove that the sum of two consecutive odd integers is divisible by 4. Well, if you took a closer look at, the situation that was given to us in part A, you can see that 2n minus 1 and 2n plus 1 are consecutive odd integers, right? Because if we have 2n minus 1 and then we add 1, right? So then we get 2n, and then we add 1 more, we get 2n plus 1. So these are like odd consecutive integers. So this and this is obviously odd consecutive integers. So this is odd, and this is odd, and this is even, right? Obviously, I didn't mention 2n minus 1 can also be odd, but yes, it can be considered as odd. And 2n plus 1 is obviously also odd, right? So now we can use, the information that we have right here and, move forward, right? So if we do that, that technically we're going by the hence property, right? So if we do sum of two odd consecutive integers, right? That's 2n minus 1 plus 2n plus 1, right? So if we add them up, what are we getting? 4n, right? It simplifies to 4n. Now, basically, what we're trying to prove is that it's divisible by 4, right? So if it's divisible by 4, it must be a multiple of 4, right? Which it is, right? Because it's 4 being multiplied into any variable, right? Variable or integer for that matter, right? If it's a multiple, or if you could factor out a 4 here, right? It is divisible by 4, because if I divide by 4, what we get is n, right? What we're getting is n. And because it's, dividing cleanly with no remainders, right? We can say it's divisible by 4, right? Hence, divisible by 4. Now, if you thought of it, a different way, one different way could be, you can think of it as 2n plus 1 is one odd number, right? Another odd number, how can you get? If you add 2 to this number, right? If you add 2 to this number, you get another odd number. Okay, right? If you add one to it, then you get 2n plus 2, which is an even number, right? Why is it an even number? Because if you factor out a 2, you get n plus 1. And it doesn't matter what this is, right? This is irrelevant. Because it's being multiplied by 2, the entire expression is being multiplied by 2. It's an even number, right? But here that's not possible, right? Because if we do 2n plus 2 plus 1, right? So what do we get? We get n plus 1 plus 1. So this itself could be treated as a different thing, right? If I put this in a different color, maybe, right? This could be different things. So this could be 2k plus 1, and thus it's an odd number, right? Now you see where I'm getting with this, right? I'm again, I just proved that 2n plus 3 is an odd number by, breaking 3 into 2 and 1 here. And then I show that it's an odd number, right? So now let's go back to blue. And now, so if we took 2n plus 1 and 2n plus 3 as our odd consecutive integers, no problem with that, right? So let's add the like terms here. We get 4n plus 4, right? And then what do? We factor out a 4 again, right? Obviously in this one, it isn't that, that obvious. I just put the parentheses just for the sake of them. But here, if we do that, we get n plus 1, right? Again, this part is irrelevant, completely irrelevant. We don't care what it is, right? Because all we care about is the fact there's a 4 outside. So That's all that really matters to us. And because there's a 4 outside, it shows that it's a multiple. K is a multiple of 4. We can say that, right? Or this entire expression is a multiple of 4. And because it's a multiple of 4, if we divide by 4, it'll divide evenly with no remainders, and thus it's divisible by 4, right? I just showed you guys two different ways with which you could have approached part B, right? Again, you want to do this, you want to do that, doesn't really matter. But again, it said hence or otherwise. That's why I did this part. Other if you only had hence, then we would have to do this one, right? Okay, so that was this example. Next example. Show that this expression is equal to the right hand side, right? So it's a simple LHS is equal to RHS part. So let me change the color. Let's take light purple. Okay, so all we have to do is show that LHS is equal to RHS. That's our entire goal here, right? So let's do that. I mean, the simplest way we can do it is, I guess, just simplifying this, and just adding it again and again, right? We can do that if it's a paper two question, right? It'll take hardly a second to do it if it's a paper two. Use your calculator. But if we don't, right? I mean, how are you gonna simplify it? You can take the common denominator as 64, and then multiply all of them according to 64 and then simplify them. You could do that, sure. But if you take a closer look, this looks like a geometric sequence, right? 1/2 minus 1/4, 1/8 minus 1/16, 1/32 minus 1 upon 64, right? It looks like a geometric sequence to me, or I would say geometric series because there's operations here, right? So what I see here is U1 is 1/2, and the common ratio is minus half, right? If I do minus 1/4 upon half, I get minus 1/2. Now, don't do 1/4 by half, right? Don't do that. Technically, this sequence is actually 1/2 plus minus 1/4, right? And then plus 8 plus minus 1/16, right? Just be aware of this. Don't neglect the minus sign. It's very important, right? So we have our common ratio. We have our first term, right? And because the common ratio is the modulus of the common ratio is less than 1, we have a sum to infinity, right? So we have sum to infinity, which is u1 upon 1 minus r. So now if we use this formula, what do we get? We get 1/2 upon 1 minus negative half. So we get 1/2 upon 3/2, right? So the 2's in both cancel out. So we're left with 1/3. Hence, LHS equals RHS. And it's proved. Right? It's a very simple, straightforward thing. This will probably be like worth 3 or 4 marks in a paper if it ever comes. But I just showed you guys how a direct proof is brought into play by using another concept of sequences and series, because I did that because we previously did sequence and series, so I thought it's appropriate to bring it in, right? I mean, you can have a similar thing with trigonometry or vector algebra or 3D geometry as well. When you have equation of a line or a plane, something like that, maybe it says show that it intersects in one position or only at one point, or it doesn't intersect at all, right? Technically, you can even have that, right, with functions or calculus, anything for that matter, right? Direct proofs can be incorporated in any chapter, right? I mean, I could have taught, I could have explained this at the very end when we have finished the entire syllabus, but I just did it because you can apply it later on as well. It's not some rocket science thing. All right, let's look at this example. It says show that LHS is equal to RHS, and then hence determine the value of 1/5 minus 1/6 plus 1/7. So, like I mentioned previously, we have expression which with only hence, right? There's no otherwise. So we have to use this to solve this, right? But again, we have a bit of leeway here because we're already given the answer. Had this not been given to us, this part would have been not this wouldn't have been possible to solve. So technically, even if we can't simplify this or we can't even do part A, you can still do part B and earn some partial marks, right? And I'll explain that once I do the entire question. So for those, for if you ever come across a question where part A is just impossible to solve and you're not able to make anything out of it, and if part B does seem reasonable, how can you, earn those easy marks, right? Anyways, let's get started with the question. So again, it's a very simple LHS is equal to RHS, right? So all I have to do is LHS is equal to RHS, right? So what I'm going to do is I'm going to write LHS here to show that I'm going to simplify LHS. So I'm going to write it here again. 1 upon n minus 1 minus 1 upon n plus 1 upon n plus 1. And I'm going to use my RHS as a guide. When I have the RHS given, right, when I have the answer or what they want to see, I should use that as a guide every time. So here you can see that they've taken n, and this can be broken down actually. This can be written as n plus 1, and n minus 1. So for those of you who didn't pick it up, right, that's what's happened here, right? So they've taken a common denominator by multiplying each of their denominators, right? That's our common denominator. Okay, this is our common denominator. So let's, multiply with the common denominator everywhere. And what we get is n plus 1 times n upon n minus 1 minus n plus 1 into n minus 1 upon n plus n times n minus 1 upon n. And I'll write it as n squared minus 1, and then n squared minus 1, and n squared minus 1, right? That's what I've done here. That's it. So what I'm going to do is I'm just going to focus on the numerator, right? I know the denominator is already matched with the required RHS part, right? So I'm just going to focus on the numerator. Now, if I do that, what I'm going to write is I'm going to write n plus 1 minus n plus 1 times n minus 1 plus n times n minus 1. So what I'm left with is n squared plus n minus n squared minus 1 plus n squared minus n, right? All right, there's no need for this. So now, simplifying it a bit more, what I'm left with is n squared plus n minus n squared plus 1 plus n squared minus n, right? So minus n squared plus n squared cancels out, and n and minus n cancel out. What I'm left with is n squared plus 1 upon, this is the numerator, remember? And n squared minus 1, right? So I'll just put in a different color right here. So right here, right? So we just did LHS is equal to RHS. Right? LHS is equal to RHS. So now what we can do is we can go ahead and solve for the second part, right? Which is just asking us to find the value of 1 by 5 minus 1 by 6 plus 1 by 7. Now, you can't just do normal, arithmetic and solve it, right? That would be incorrect, right? The examiner will not give you any marks for that. You have to use the previously, solved, material and use that work with that, right? So now, if you notice that these are like consecutive numbers, right? Look at it. Just focus on the denominators. What do we have? 5, 6, 7, right? So what we have is something like that as well. N plus 1, which is 1 greater than n, and 1 less than n, right? So we have something like that. It's matching with the conditions that is given, and we know that the sum of this is kind of like the sum of the, right? So we have n here maybe, right? We have n plus 1 and n minus 1, right? And it's equal to this part. So all we need is just the value of n, and we just plug in the value of n, and we get our answer. So here, n is not 5, it's not 7, it's actually 6, right? Because it matches with the condition. N is equal to 6, right here. Another way you could have done it, if suppose you just didn't have 1 upon n, right? If you didn't have that, what you could do is, take this part and 5 and then equate it together. So you have n minus 1 is equal to 5, and then you would have n is equal to 6, right? That's another way you could have done it. I'm just telling you this. Obviously, it's not necessary in this question, but if you have some other question where n, there is no direct value of n which you can, correlate with. So you can use this method every time to do the same thing. Okay, so now that we have the value of n, all we have to do is just plug it into, n squared plus 1 upon n times n squared minus 1, right? So if we just plug it in, what do we get? N is equal to 6, so 6 squared plus 1 upon 6 times 6 squared minus 1. So what we get is 37 upon 6 times 35. Okay, so you can leave it at that. If you want, you can simplify it a bit more. I'll just simplify it. So we have 37. I'm gonna break this, right? Suppose I have to solve this quickly and I don't want to waste a lot of time. So instead of doing 35 times 6, I'm not gonna do that. What I'm gonna do is I'm gonna write this as 3 times 2 times 35. So I know this is 70, right? Because it's quite easy to know that. So we get 37 times 3 times 70, and then we get 37 times 210. So this is our final answer, right? So 37 upon 210 is equal to part B, right? That's the answer for part B. Now, like I said, before I started this question, suppose we couldn't do this, then what do we do? So if you couldn't do that, what you can do, or what you could have done is you would have had to find the pattern here, right? You could have seen that, okay, these are consecutive numbers in the denominator. So it corresponds with this, and it's telling you that it's equal to this. So this part was also equal to this, provided we get the correct n value. Again, you could have determined the n value, it's equal to 6, and then done the part in lime color right here, right? And then you would have been awarded complete marks for part B, right? So yeah, this was direct proofs. This was the last question for direct proofs. Like I said, not a lot of questions. What I wanted to get from this video, or what I wanted to show with this video, is the different applications, or the different techniques that you can apply to at least get maybe some marks, like I just showed in this example, like in this example, or get all the marks, obviously. So these are just the techniques that you should keep in mind when you do questions from the textbook or the past papers, right? And again, this is kind of a practice. Like I said, it's a skill based chapter, not a more of a conceptual based chapter. So the more questions you do, the more different types you'll come across, and the better you'll be at this chapter. But again, don't stress on it too much. The weightage is quite low, right? You want to do it right now. You want to practice direct proof questions, a few direct proofs from the textbooks. You have Oxford, you have Hayes, you have Cambridge, you have Pearson. You have loads of different resources for that matter. And you can do that. And then, do past paper questions if you feel like, if you find them. I don't think there are a lot of direct proof questions anyways. There are quite few, right? And they're usually with another question, right? They're not a question within themselves. You won't find one 6-mark question which is a direct proof question. It'll probably be part B or part C of some question, which is maybe worth 4 or 5 marks, right? So that's how direct proof usually comes along in papers. And yeah, so that's about it. Like I said before in the previous video as well, do it right now, and then forget about it, and then when you come across past papers, that's where you really apply it, right? So that was all for direct proofs. Next video we'll take a look at mathematical induction, and yeah, so I'll see you in the next one. Bye bye.